So the first one is a Venn diagram problem with A, B, and C defining certain types of workers, certain where they work, age, and whether they have a particular malady or not, bronchial problems, and then the universe of 300 workers. So what I thought the best way to do it would be to give you an exhaustive list here of all the conditional probabilities, unions, and intersections, and then you ask you to describe them, because that's really what's important with this is being able to verbalize what it means, as always. So let's take a look at the solution set, and I organized it in a particular way because of the use of each one. So the probability of working in a paint shop, these are pretty straightforward. They all have the total universe as the denominator. Okay? So there's 75 out of the 300 work in a paint shop, 150 out of the 300 are over 40 years old, and 25 out of the 300 have bronchitis. Okay, so that's just straight probabilities of belonging to the three sets, A, B, and C. Then I said, given that a worker, let's see, B is 40 years old, what's the probability that they work in the paint shop? So that's the conditional probability. Probability of working in the paint shop if you're over 40, okay, or if one is over 40. It's the best way to verbalize that, I think. And that's 30 out of 150 because we're only looking at 150 people who are over 40 years old. Okay, so we know that we're already restricted to set B, the over 40-year-olds. So that's our denominator. Then from that point on, because you have the probability of being in each of the sets, you have all the combinations of the conditional probabilities that would be of interest. We don't need to calculate the intersection and the union other than from those probabilities themselves. We don't have to go back and use logic to try to figure out what the denominator should be, etc. We can just use the formulas. So the intersection of A and B is A given B times the probability of B. Okay? Or it could be B given A times the probability of A also.
Same answer.
Same answer, yeah. And that's the probability of working in the paint shop and being over 40. So that's and. Because the intersection means that you have to be a member of both sets. So it's and. The union is or, because you could be a member of either set. Okay? Or, so that's the probability of A, in other words, the probability of working in the paint shop, plus the probability of being over 40, but then you have to subtract off the intersection because you don't want to overcount it, right? So that's the probability of working in the paint shop or being over 40. And we get a fairly high probability with that because there's, out of 300 people, there's 225 that are in the paint shop, that are in the paint shop and are in, or are in the over 40. Okay? That accounts for 225 people, so we would expect a fairly high probability. Same set of logic for the other conditional probabilities then. Okay. Is everybody clear about when to use and or in relationship to the set notation and what the conditional probability means? Because I don't want to dwell on that. It's just, but I wanted to give you another exercise. Yes.
I just checked to see if I would get the same answers doing it logically and just doing addition and subtraction from the Venn diagram, and I ended up getting the same values, which makes sense. If we ended up opting for that method, if we find that more useful or clear.
Unless I tell you exactly how to do it, which I won't. Do it however is useful, is easiest for you.
Okay.
Yeah, so that goes to, if you prefer to, I prefer this because I don't think about it as much, but if you prefer to count them and then take the probabilities from that, that's fine too, doesn't matter. Okay? All right, then I went way overboard on bays, as you probably noticed. 2, 3, and 4 are bays there in questions. For the first one, information transmission scenario, we have 2 types of signals. Okay, so we divide the universe into those 2 types of signals, and then received, because the signal can be either received or not received. So that will look like a pretty simple Venn diagram. It looks like this. This is type 1, this is type 2, and this is the probability of being received from here. Okay. And I know that this is 0.8, and this is 0.2, which should add up to 1. All of those should add up to the total probability. And then type 1, the type 1 signals are received 0.4% of the time. Okay. So that's the conditional probability, given that it's type 1, the probability that it's received. And then I know type 2 signals are received 0.04% of the time. So given that it's type 2, the probability that it's received. So I can calculate the probability of it being received and and then the converse of the converse of the conditional probabilities. So these are the given ones, right here, right here, right here, right here, and these are the ones that you need to calculate by manipulating the Bayes formula. Does everybody see how to derive each one of those equations? Is that, if that's a problem, let me know, so we can talk about it some. Because this is really an intersection problem where you set each of the possible equivalences for the intersection equal to each other. And you know three out of 4 so far of those equivalences. We know probability of being received. Well, first of all, we calculate the probability of being received from these. So this, we sum up both of those, each one times its own probability, and that's what we get probability of being received. And then we know 3 out of 4 for each one of those equivalencies. If you would like to see me derive those, let me know. If that's pretty clear, that's okay. We don't need to go into detail. Speak now or forever hold your peace. Okay. I didn't do a drawing here.
Excel for B and C, like they perfectly added up to 1. Then in my rounding, it added up to like 1.01. And I just, no, for the last two, 0.9756 and 0.0244. But when I did by hand, it was just off of 1. Is that going to be a huge problem?
No. I'm not going to.
Okay.
I mean, within something like this, within 1 or 2 hundredths of a point, probably.
That's all it is.
Yeah. Okay. Let's take a look at the second one then. Formulation of it a little bit. Formulation. The second one is electronics assembly plan. Since I didn't apparently give you the drawings, I'll draw them. 35% of the assemblers took PCBs. Okay, so we have a universe. I think there's 3 here. 4 units of mask, and the remaining gets 3 groups. So coders, maskers, and ICs. got 35% of these guys, and we got 40% for here, and that leaves 0.25 here. And what we're wondering about is the prevalence of upper respiratory disorders. So this is our URD, and we are given that among PCB coders, given that they're PCBs, among coders, that one is the probability of URD given PCB. This one is prevalence, probability of URD given masking, and this one is prevalence of URD given IC. Okay, this one we know is PCB is 2%, so that's 0.02. The demaskers is 0.6%, so it's 0.006. I got my point.
Next.
Oh, the next one, yeah, and the next one is the IC installers is 0.3, so that's 0.003 probability. So we know the conditional ones. We can calculate the probability of an upper respiratory disease, and then do the conditional probabilities from there. And that's what each one of those look like. Same thing, except now we have 3 divisions rather than just 2 categories for the universe. And then for the third and final, factory 2-inch springs, 4-inch springs, that's another one like number 2. We have two divisions of the universe into 2-inch springs and 4-inch springs, and we have a defect rate associated with them. Actually, I did a drawing for that one. So that's what my drawing looks like. That's what probabilities look like. This is very similar to the one that I did in class. Okay, just different names, different probabilities associated with each one. All right, so let's put Bayes behind this then, more than enough Bayes theorem. Human operator, 1 error for every 20 attempts, so that's 1 in 20 is our P. And we can call it lambda to approximate. Probability of an error on the next attempt, that's a Bernoulli distribution, and that's simply 1 in 20, 0.05. The next 16 attempts is probability of no errors, that's binomial, and we calculate just for x equals 0, what is the probability of at least 1 error, that's 1 minus the probability of 0 in binomial. Distribution that approximates is Poisson, and same calculations that we did with binomial. We used Poisson, and those are very similar to each other. The results are very similar because it's approximation. The Bernoulli probability of 0 is 0.4401, and the Poisson probability of 0 is 0.4493. We're all the way up to the thousandth place before it is different. Pretty good approximation. Okay. And then likewise, the probability of at least 1 error comes out to be very, very similar, 0.5506, and this comes out to 0.5598. Again, that's a thousand. The chi-square confidence intervals on the on lambda is looks like this. Remember, F is 1 in 20 because 1 error in 20 attempts, and then alpha, as always, unless otherwise specified. Probably won't specify anything other than 0.05, so you can stick with that. And that's our 2F plus 2. That means that the mean attempts between failures 4.2. Makes sense, 1 in 20. 95% of the time. And for the two-sided interval, the lower limit is 3.6 because we're actually at 97.5% of the time. It's going to be, the mean time between failures will be at least 3.6. And it will be 97.5% of the times less than 790. That upper one isn't a very interesting result. And we can't really use that for much most of the time. But that's what it looks like. Does anybody have trouble determining what FNT is? I probably should say that slowly, it doesn't sound good. But what those two values should be. Okay, good. All right, probability that the first error will occur on the 6th attempt. This was probably a mistake putting them in the same order each time. I was lazy because I don't want you to get used to order. They won't be in any given order on the exam. And they won't be sections of the same question. Each one will be by itself. So that's geometric. The next one is negative binomial Pascal. And the next one is, the next error will occur on the 9th attempt is cumulative exponential. And the results, like I said, once you determine that, the results are fairly straightforward. 4 categories of flight status. Let's look at number 6. That is obviously a multinomial. And the results look like, I should probably show you at least the results for the multinomial. That was our geometric, our negative binomial, exponential, and our multinomial. This is the a priori probabilities. You have to distinguish between the a priori probabilities. I got to fix that too. But I saw your other note. Thanks, Vince. I'll fix both of them. So you have to do your a priori probabilities first, and then the upcoming distribution that you're interested in of events. And then from that point, once you've done your categorization, plug and check. And that's where you get your probability. It's more accounting. First thing you need to do is determine what your distribution is. Then you need to account for what all your values are and get use the right numbers for the right formula, the right variables. The hypergeometric. The next one again. Oops. If I'm doing without replacement, I have capture 60 marbles, 20 green and 20 blue, all 5 the same color, without replacement. Probability of drawing all 5 red, or all 5 green, or all 5 blue. I was looking at my answer there. I think that it should be 3 times because there's 3 different ways. So I don't know what I was thinking when I did that. So I think it should be 3 times 0.0028 because there's 3 different ways to get that, and there's no intersection, so we should add them all up. So it's another one I got to fix. But anyway, I probably won't try to be clever on the exam. I'll just give you something like that to calculate. Let's look at the way, the wording of the telephone calls arriving at a rate of 2 per minute. Okay, there we have a lambda of 2. That's more than one. So I did give you at least one problem. Probability that 6 minutes will elapse before 5 calls arrive. We have a lambda for each call. We have 5 calls, so that means that R is 5. So this is a more complicated gamma, and the gamma has 5 terms now: 0, 1, 2, 3, and 4. And this is what you end up for the generic equation, and for each of the terms, these are the values. Add them up. But notice the way I worded that. I said, what is the probability that 6 minutes will elapse before 5 calls arrive? So that means the probability that's going to be greater than 6 And that's why you have to watch out for that, because that's why we're looking for the upper tail of the distribution. You don't subtract, you don't say 1 minus. Because 1 minus is the lower tail of the distribution, less than or equal to. Greater than or equal to, or greater than, same difference since it's continuous, is not 1 minus, it's just the reliability. It's just that part of it. So now we have a small probability, right? And if you go back and look at the statement, 2 per minute, I would expect to have 12 calls on the average in the next 6 minutes. What's the probability that 6 minutes will elapse before 5 calls arrive? That's a low number of calls given that average. So I would expect a small probability. Now, if you look at the opposite end of it, the opposite part of the distribution, it answers a different question. Let's look at 1 minus that. That's a very high probability. That answers a different question. Instead of what's the probability that 6 minutes will elapse before 5 calls arrive, what's the probability that at least 5 calls will arrive in 6 minutes? And that's a high probability, okay? So it's a little bit different. And that's what you'd expect, because I'd expect 12. So the probability that 5 will occur is a high probability, and it is. It's over 99%. And does everybody see the distinction? It's a little bit subtle, but it's important nevertheless. So watch out for that. And then another plug-in chart that I ran across. Textbooks, where I was looking for, I looked at often to get these examples, these questions. I look through textbooks because I figure they've already, they're experts. Is anybody who writes a textbook on this knows more about this than I do, I figure. So I go into the textbooks to look for their problems, because I figure they've taken the time to write problems, and they are better than the ones I can come up with. The Weibel distribution had a truly pathetic showing in all the textbooks. I learned more about the Weibel distribution on a systems reliability website than I did on most of the textbooks I looked in. Now this is an example of the types of problems I came up with. They really weren't very helpful. I used it because I lacked some imagination at the time, but it's not a very helpful, it's not a very informative one. Because with the Weibel distribution, like I said, the way to think about the Weibel distribution, and let's go take a look at this, is to think about it in terms of when the failures will occur in the bathtub curve. And you really can only adjust the failure rate, the alpha, the shape factor, you can only adjust that from empirical data. And even then it has a range. I mean, they give ranges for the shape factor, and they also give ranges for the MTBF. Okay? And when you're dealing with real data and collecting data, you're going to get variability. That's inherent in data. So really what you need to think about is, if I have, is it something that from my data implies that they fail early, in which case that's what my shape factor is going to look like, or is it going to occur later, in which case my shape factor will be greater than 1. Okay, 1 being the deflection point, okay, because that's just a straight exponential. Okay. So having said that, we can look at alpha. We can look at alpha as 4. In other words, 4 is probably the waves are going to occur later in their cycle. Put it like that. What's probably a wave height between 5 and 10 feet? Okay, and if the average height is 8 feet, that's the mean height, or the mean MTBF. So if then you would do less than 5 and less than 10 and subtract the results. That was the interesting part of it. That's why I included it at all. It's had a slightly interesting bent to it. Okay? We just calculate each one of those and subtract the results between, because that is a cumulative distribution function for the Weibel. Okay. All right. That is the problems that I came up with. Did anybody come up with any other burning questions while I was going over these? If not, I will entertain, I gotta go look at my calendar, I forgot to a while ago, I was doing something else. I will entertain the idea of doing a review. Either Monday, I prefer not Tuesday, but let me look at my calendar real quick, I'll be right back.